Assalamualaikum and greetings to Dr. Jeff. We are from group 4 and this is our SEL video. So I will be first presenting about SEM for the vaccine. So as for only the nanoparticle, which is my SLN, it will only be we can only see a sphere under the SEM. But if we were to encapsulate the SLN with drug like mRNA, it should be slightly larger than the my SLN. For example, my SLN is 50 nanometer in diameter. The my SLN and mRNA should be 100 nanometer. And if you were to view mRNA under SEM, it should only be strands, small strands. Okay, so you cannot see the internal structure with SEM, so you do it with EM. Okay, I will pass to the next presenter.
So we go to the TEM, which is the transmission electron microscope. So for definition, basically TEMS is a work by a beam of electron will be transmitted to an occurring sample and interact with the specimen at its pass through. So from the TEM, basically we can view the sample at atomic level. So here we can see that for my SLM, we can see the says that, and for my SNN receptor, we can also see the morphology, the size, and the crystal structure of it. So next.
Okay, before I start, my name is Myra Balki Binti Syahrir, method number 203093. So moving on to FTR, which stands for Fourier Transform Infrared Spectroscopy, which detect the free functional group in the same sample as well as kinetic movement of atom that caused by infrared photon absorption. So each atom in the functional group only absorb a specific wavelength where the intensity of an infrared beam is measured before and after it interacts with the sample as a function of the light frequency. So as you guys can see on the graph, the x-axis indicates for wavelength while the y-axis indicates for the transmission. So the first lane is the wavelength of the MySNN, where it detects three functional groups such as nitrogen, hydrogen, carbon, oxygen, and also carbon double bond oxygen. The second wavelength is the MSLN, encapsulated with mRNA. And lastly is the wavelength of mRNA, where it detects three functional groups such as SLN. That's all for me. Thank you.
Rahman, and I'm from Team D. So DLS and PDI will be presented by Kur, and I'll be presenting the zeta potential.
Well, okay, for the DLS, you can see here that there's several graphs for MySLN and MySLN encapsulated with mRNA and also mRNA. So we can see here that MySLN has the graph is based on the intensity and the size. So MySLN has the smallest size in diameter, because there's nothing in there, and then once it encapsulates with mRNA, there'll be an increasing in the size. However, the peak is not as high as the MySLN only, and you can see there that for MySLN and mRNA, there's two like wavelength, because we assume that there's not every mRNA is encapsulated in micellin. There will be like half of it or like some of it which is empty. Hence why there's small graph at the micellin. And then for just only mRNA, you see that diameter is the biggest because the mRNA tends to accumulate together. Hence, they clump together, hence forming a bigger size. For the PDI, we assume it to be around 0.7 something because we don't want it to be too high but not too small, because we can see that the PDI is based on the several wavelength of the GLS. That's all from my part.
Okay, next for the zeta potential, my group mates evaluate the charge of the particles at certain pH, which is pH 2, pH 7, and also 11. So the basic of zeta potential is that the addition of acid, which means that acidic pH will accumulate more positive charged molecules, and at basic pH, it is more towards the negatively charged molecules. So at pH 2, the positively charged molecules are more present in comparison to negatively charged molecules. So the mRNA is negatively charged while SLN is positive. So if the mRNA is incorporated in the SLN, it is more towards the positive charge. Next, at the neutral pH, the mRNA and SLN will be going to be around the same amount. And once we encapsulate the mRNA into SLN, the charge will approach to 0. And lastly, at basic pH, there will be more negative mRNA compared to and less positive SLN. And after encapsulation, the charge is more towards negatively charged particles. So that's all from us. Thank you.
Okay, hi everyone. My name is Nur Ain Shuhada binti Abi Razak. We matrix number 200993. So for my part and Farah is about to detect the special cell that will undergo apoptosis using FMY, SLN, mRNA. So for the next picture. Okay, for the FTIR spectroscopy. So before that, we need to know what are the spectra for the MSNN and mRNA. So we can see that for MSNN, they are wavelength at 3,600 to 3,200, and also from 2,000 to 1,200. So this both represents the hydroxyl group and also the C double bond O group. So for mRNA, we can see they are triple bond and also hydroxyl, and also there's a triple bond. A triple bond exists in the 2000 wavelength, and also for 3,600 and 3,200 is for hydroxyl group. So since we want to detect the cell, we put the fluorescence in the solid lipid nanoparticle. So from that, the spectra will be, there will be the new spectra, which is a triple bond. There is a triple bond, hydroxyl bond, and also double bond. So when we put in the body, and this FMY, SNN manage to detect the specific cell, so there will be the another spectra formed in the transmission. So we can see that there are difference between FMY, SNN and FMY, SNN, mRNA. So the new bond form is the single bond, and alongside with the triple bond, double bond, and also hydroxyl bond. So I pass to Farah.
Okay, Thank you. My name is Siti Farhani binti Al-Hafiz. My matrix number is 202499. So to test for the cytotoxicity of the COVID-19 vaccines. So since the cell are said to be undergo apoptosis, so we assume the best assay to use is Annexin V5. So for Annexin V5, it works by conjugated with the FITC4, where it binds to the phosphatidylserines. So these phosphatidylserines only exposed to outer membrane when they undergo a early apoptosis stage. So when during the early apoptosis stage, the FITC will conjugate to phosphatidylserines or in short PS. So we can observe the green fluorophore in their plasma membranes. So the quantifications analysis is presented as shown in the graph. So our result shows that the FMY SLN mRNA shows the highest amount of cytotoxicity and hence produce the highest amount of apoptotic cells. Thank you.
Okay, hello everyone. Now I will explain about transmission electron microscopy and also scanning electron microscopy. For the first one, as you can see in TEM, for my SLN, the size will only show 50 nanometer, and it will only show the blank one. Then if we put inside the mRNA, it have two colors. So mRNA will become more darker compared to my SLN because more electron passes through. And then lastly for mRNA, it's only like that one. For the scanning electron microscopy, we can only see my SLN surface, and then for my SLN mRNA also the surface but different in size, and lastly mRNA with that size. That's all, and then I continue with Diana.
Okay, so for the FTIR spectra, as similarly explained by Umaira, so basically FTIR, the purpose of this is to use infrared to measure the free functional group present in the nanoparticle. So if you see this in these characteristic wavelengths, there are your nanoparticle should possess some peaks that are similar to at least one of its components. So in this case, the mRNA has a peak somewhere over here, and your nanoparticle with the mRNA should also have that peak, and there are some parts where it possesses the peaks of the mySLN, and like this part here. So that's essentially the fundamentals to observing the FTIR spectra. And these peaks are basically denoting to the kinetic movements that is formed from the absorption of the infrared by the free functional groups. And it manifests through the kinetic movement, and you can see it through the peaks here. And it's not shown in this graph, but sometimes you will see a peak that is not possessed by either one of the components from either mRNA or mySLN. And that is maybe due to the fact that the functional groups are no longer free and is involved in the reaction from the mySLN and the mRNA. So yeah, that's just it for this part. Thank you.
So you guys have any questions? If no?
No.
No. So I think we end our presentations here. Thank you and good luck.
Thank you.
Everyone.
Thank you.